Okay, I just want to take a few minutes and go back over the first set of notes that we did on limits in case anybody wants to watch it. I just pulled up my outline here so I could save us some time. So I just want to talk about the definition of a limit. It says if f of x becomes arbitrarily close to a single number. Now arbitrarily close means really close. All right, to a single number, we'll just call it L. As x approaches some value of c from both sides, the limit of f of x as x approaches c is L. All right, so here's our notation. All right, so this is read the limit as x approaches c of f of x equals L. Okay? Now, we'll get back to that in a second. So I wanted us to start by sketching the graph, all right, of this rational function. But to save us time, I already did that, and so I'll walk us through it. In order to sketch the graph of this, we first need to think, all right, because it has a bottom, x is not going to equal 1. The problem is we need to decide if that's an asymptote or a whole, okay? And so because we can factor x cubed minus 1, and then the x minus 1 cancels out, okay, then this x equals 1 is a whole. All right, so I have a reduced function, but I have a whole at x equals 1. Now, a whole is really a point, so I need a y value to go with that x value. All right, so I actually plug the x value in to the reduced function and got 3. So now I know my whole is at exactly 1, 3. Now, I already know that there's no x-intercepts because to get an x-intercept, I would have to take the reduced function and set it equal to 0 and attempt to factor. All right, but I know because it came from a cube, it doesn't factor, and because it came from a cube, it will always give me an imaginary root. So that just has no real solutions, so there's no x-intercept. And then for my y-intercept, remember you plug 0 in for x, right up here in the reduced function, and you get 1 for your y value. Okay, now I also spent some time finding the vertex, and if you need a refresher on that, you can come to my office hours. All right, so I plotted the vertex, and then I plotted the y-intercept, and then I just made a symmetric point to that. Then I plotted my open circle and made a symmetric point to that, and then I drew my parabola. And I knew it was going to be a parabola because the reduced function is quadratic. Okay? So now that we have that graph, I want to talk about it. It says even though there's a hole at, all right, 1, 3, I want to know as x approaches 1. Okay, so like I'm thinking, all right, here's x equals 1 as I come into that x value. But again, I have to be on the curve. So as I come into an x value of 1, okay, and that's not supposed to be like, hold on, that's not supposed to be like an asymptote or anything. But as x approaches 1 on the graph, okay, what y value are we approaching? All right, so even though there's a hole there, the graph is coming into the same y value from both sides. All right, so because we're coming into a y value of 3 from both sides, we can say that the limit as x approaches 1 of the original function is 3. Okay, now, what if I wanted to confirm that with a table? All right, so what I've done is I've given you, there's supposed to be an f of x there. So there's my function, same function, and I want you to plug these x values in for x in that function. Now again, if you need help on the calculator, you'll just need to come see me on office hours and I can go over that with you. All right, but the idea is that these numbers are getting closer and closer to 1 from the left, and these numbers are getting closer and closer to 1 from the right. Okay, and so I'm going to pause the video and fill in the values real quick. So I'll be right back. Okay, so now the values are filled in. And again, what I want you to notice is that as the x values get closer and closer to 1 from the left, what number are the y values getting closer and closer to? And then the same thing from the right. Okay, look at your y values. They're both getting closer and closer to 3, even though there's an error at exactly 1. Okay? So as the y values get closer and closer to 1, f of x got closer and closer to 3. That's a y value. And so that's another way to say that the limit as x approaches 1 of that function equals 3. Okay? All right. So then on the back, or on the next page, we have another one. I changed the function. I don't know why my f is not showing up, because it's definitely on my paper. But again, this is where you're going to practice with your calculator. Okay, so I'm going to put it on pause and fill in all those values real quick. Okay, so now the table is filled in, and I did keep some extra decimal places just because there were so many 9s, and I didn't round them off because I wanted you to see the pattern. But as I come into 0 from the left, because I want to find the limit as x approaches 0 of this function, I have to approach it from the left and the right. Okay, so, well, when you're on 0, the left are negative values. Okay, so they're really tiny, but we're getting closer and closer to 0 from the left, and then I need to look and see what y value am I getting closer and closer to. Okay, and then I do the same thing from the right and pay attention to what y value. So even though there's an error at exactly 0, because I'm getting closer and closer to 2 from this side and closer and closer to 2 from this side, the answer to the limit is 2. Okay? And then we could look at the graph on our calculator to make sure that it confirms. I just want you to understand that your calculator, the pixels, are not going to show you the holes. All right, so I'm going to draw you a real quick sketch of what this would look like. All right, let's see. It would have an end point, which would be kind of hard to find, at -1, 1. And then it goes up and over like a normal square root function. That was really sloppy, but it has a hole at 0, 2, okay? And so again, I can look at the graph, and as I come into 0 on the graph from the left and the right, I'm approaching that hole, but that has a y value of 2, okay? And so that's why the limit is 2. All right, then I gave you a piecewise. I want to find the limit as x approaches 2 of f of x given this piecewise function. All right, now, I think it is easier to draw a graph to help you. So that's what we're going to do. All right, and so it says f of x equals 1 anytime x is not 2. Okay, so x equals 2 is right here. And the graph of f of x equals 1 is just the line y equals 1. All right, so I am the line, the horizontal line, y equals 1, except when x equals 2. And then the second piece of the piecewise says when x does equal 2, I'm 0. Okay, so this notation is literally just a point because it only has one x value. All right, so there is my graph, and I want to find the limit as x approaches 2 of my function. All right, so again, I need to be on the graph, but I need to be getting closer and closer to an x value of 2, and I want to know what my y value is getting closer and closer to. All right, and so even though there's a hole at exactly 2, the limit is only what is it getting closer to. All right, what y value are we getting close to? Well, we're stuck on 1 the entire time, so the limit is 1. Okay, you can also confirm that with a table if you want. All right, now, real quick, I want to talk about there's 3 times when a limit does not exist, okay? And so if the left-hand limit does not equal the right-hand limit. So I actually gave you a function, I gave you the graph, and it says, what is the limit as x approaches 0? All right, so here's x equals 0, and from the left, I'm on y equals -1, and on the right, I'm y equals +1. So because I'm not approaching the same y value from both sides, we say this limit does not exist, and you have to give a reason. And you can abbreviate left-hand limit not equal to right-hand limit. Okay? All right, next example, when a graph has oscillating behavior. That means the graph bounces back and forth so quickly that every time you get closer and closer to whatever value you're approaching, sometimes it's positive, sometimes it's negative, and it just keeps bouncing, bouncing, bouncing. So that's what's happening here. This is bouncing really fast, and this, whoop, and this side is bouncing really, really fast, the closer and closer I get to 0. And so we would say that one does not exist because of oscillating behavior. So anytime you say that a limit does not exist, you have to tell me why. All right, and last but not least, unbounded behavior. That typically means there's asymptotes and the graph goes off to some sort of infinity. All right, so here we have the limit as x approaches 0 again, but our function is 1 over x squared, which hopefully you remember has an asymptote. It's really sloppy, but it has an asymptote at x equals 0 because the bottom's not allowed to equal 0, but it doesn't factor out like a whole. All right, and then we get these two curves that come in from the left and the right, but then shoot up forever, okay, and never actually get to the asymptote, okay? They get really close to it, but we can never equal 0, and we're going off to infinity. That's what's called unbounded behavior. And so again, we're just going to say does not exist because of unbounded behavior. Okay, so that's just a quick recap of what we learned on the first day of limits.